Hello, my name's Ben Holcomb. I'm an associate professor here in the School of Mechanical and Mechatronic Engineering in the Faculty of Engineering and IT at UTS. And I'm down here in our brilliantly equipped dynamics laboratory, and I'm here to talk a little bit about this 8-story tower which we have here, which is a simulation of potentially a real-world scenario. It's an approximation of an 8 rigid body degree of freedom system. We have 8 of these large lumped masses evenly distributed along the length of this rectangular hollow cross-section steel tube. So it is an approximation. This of course is a continuous system. Here's the rectangular cross-section steel tube. You can see it's a hollow tube, and so primarily the frequencies of this system are the 8 degrees of freedom, the 8 natural frequencies come about as a result of these lumped masses. This tower is instrumented with 2 DC response accelerometers. Presently I'm using an Endevco 770F MEMS-based variable capacitance transducer, and I happen to have that mounted to the 7th mass. I have another one mounted at the bottom of the tower to the 1st mass. But where exactly we mount those is not too important, because I'm going to do an experimental modal analysis acquisition campaign using an instrumented modally tuned impact hammer. This is a device from Kissler. It's got a relatively large head mass which allows me to excite the structure with a short, sharp, impulsive excitation, which will be measured by the integrated force transducer within the impact hammer. And I can rove the hammer at each of the degrees of freedom along the tower structure. I can take 5 averages, 5 impacts at each of these locations, and at the same time as I measure the force here, I'm measuring the response from the accelerometers with 2 accelerometers. I'm building up an FRF matrix by performing this kind of an experimental campaign. I have to attempt to impact the masses consistently and in the central location with a sharp blow, a little bit like we would use if we were a drummer drumming a drumstick. It's a little bit like a whipping motion, right? We're not trying to drive a nail home. We don't need to give it a massive amount of force to excite the response from the tower. For a linear system, which this is an approximation of a linear system, if we increase or reduce the excitation force, we will have a proportional increase or excitation of the response. And because it's an impulsive measurement, of course, wherever I strike the tower, I'm exciting all 8 of those resonant frequencies simultaneously. The tower is responding at 8 resonant frequencies simultaneously, and these 2 response transducers are measuring those responses at the same time. I have a bespoke acquisition system over here that's built on a National Instruments LabVIEW solution. I have hardware here, data acquisition system, USB connected system to the acquisition system here. My 2 transducers, my response transducers, are powered by this power supply sitting up on the top there. My impact hammer is an IEPE based sensor. That device is being offered signal conditioning by the National Instruments acquisition system. In software, I can start the measurement campaign by hitting the play button in the top left of this display, and then you will see I've got a scope type view in this top window, and then these are going to be my captured measurements in these 2 windows below, and I'll have a frequency response function in the bottom window. So if I take my hammer impact, I'm just going to come and strike the structure at strike 3, you'll hear some audible feedback. So there you could see briefly we had 2 response measurements here, and this is scoping, so it's now still it's buffering all the time, collecting new data. But those 2 measurements and that beep that we heard was to indicate that the measurement had been triggered based on the force measured by the force transducer, and although it'll be a little bit small in here, there's an impulsive event here on the force transducer channel, which is this red curve. The 2 curves below in green and blue here are the responses of each of the 2 reference transducers, one at level 7, one at level 1, and they're obviously different to one another. They contain multiple sinusoidal components. which you can potentially see, but of course with an 8 degree of freedom system we've got 8 sinusoids summed together, and it's difficult to be able to differentiate those from one another. So to do that effectively we use a fast Fourier transform, and in modal analysis we use a variant of a fast Fourier transform which is called a frequency response function. If I zoom in on this frequency axis, we can hopefully see reasonably clearly that there are some resonances, some peaks in the frequency response function for each of the 8 natural frequencies of the tower. 1, 2, 3, 4, and so on. And for each of the 2 different transducers, because I struck the tower at a particular location, the relative levels of those are different to one another. And the relative phases are also different to one another. To complete the measurement campaign, I will do 4 more impacts at the same location. I should allow the system to come to rest between impacts. Strike again. I'm averaging these FRFs, and the averaged FRF, albeit it's changed the x-axis, the frequency axis again, should remove any of the non-deterministic signal content from these measurements, i.e. the noise, and I should be left with just the deterministic signal content, i.e. the response of the tower. 1 more impact, and that's a full measurement set, and the software will then give me the option to save those data onto the disk drive, onto the hard drive of the device. Just zooming in again, we should see, I can't zoom in at the moment because it's waiting for me to tell it whether or not to save those data, so I'll just cancel that, but I can still see here those various natural frequencies for this 8 degree of freedom system. And those data will allow me, with processing, to be able to define and determine the modes of vibration of this tower at each of the 8 natural frequencies. And of course, because I'm a mechanical engineer, I can measure the geometry here for these masses, which are in steel, mild steel, and for the column. And I can, for example, build a model in CAD, in SolidWorks, and do a simulation to predict the natural frequencies of this tower and compare and contrast with those which I get from experiment. I hope that's been a useful video about the 8-storey tower in the Dynamics Lab here at UTS in the Faculty of Engineering and IT. I've been Ben Holcomb. Thank you.